The first type of bonding that we're going to talk about is something called ionic bonding. First, we need to define what an ionic bond is. An ionic bond is a chemical bond that exists between two different types of atoms. It's the type of bond that exists between a metal and a nonmetal, or positive and negative charges. This attraction, this bond, exists through electrostatic interaction. So it means they're not really connected. It's the attractions between positives and negatives. That's what electrostatic means. So electrostatic is between positive and negative charges. So we're going to look at how things become positively charged, how atoms become negatively charged, and then how those are attracted together to create bonds. Because an ionic bond is a chemical bond that exists between a metal and a nonmetal, or a polyatomic ion, and we'll get to those later, through electrostatic attractions. The easiest way to look at ionic bonding is to just jump in and look at an example. So the first example we're going to look at is a bond or an attraction between sodium and chlorine. So we have sodium and we have chlorine. Now, the first step to show ionic bonding is to draw their Lewis dot diagrams. Now remember, Lewis dot diagrams only show the valence electrons. Sodium, because of its location on the periodic table, we know has 1 valence electron. Chlorine, because of its location on the periodic table, we know has 7 valence electrons. So we have our sodium with 1 valence electron, and our chlorine has 7. Now, we compare these two, and we're going to look at how the atoms will achieve an octet. Remember, when we're looking at valence electrons, the goal is to get to 8, or have an octet or a full outer shell with valence electrons. So sodium, the easiest way for sodium to become, or to get its octet, is to lose an electron. It's going to lose its 1 valence electron, bump it back on the periodic table, and it'll have an octet. So that means it's going to have a +1 charge. Remember back to when we talked about positive and negative charges. If something loses an electron, it becomes positively charged. So our sodium is going to have a +1 charge. Chlorine, on the other hand, has 7 valence electrons. The easiest way for chlorine to get to 8 is not to lose its 7, but to gain just 1. So chlorine is going to gain 1 electron. And when we gain electrons, we end up with a negatively charged species. So it's going to have a charge of -1. So sodium is +1 because it lost 1 electron. Chlorine is -1 because it gained 1 electron. So now we have to show how the bonding actually happens. So we're going to show our exchange of electrons, and this is where our dot diagrams come in. So we're going to draw sodium with its 1 valence electron, and chlorine with its 7. And we use arrows to show how the electrons are going to move. So this electron from sodium is going to go to chlorine. When this happens, we end up with sodium +1 and chlorine -1. So we don't actually draw lines to show them bonded or connected. We just draw them next to each other because it's really just that attraction between the positive and the negative that's holding our sodium and our chlorine next to each other. Let's look at a couple more examples, and we're going to walk through this same process for our next 3 examples. Let's look at our next example. Our next example is going to look at magnesium and oxygen. So magnesium, based on its location on the periodic table, we know has 2 valence electrons. And oxygen, because of its location, we know has 6. Okay, so we've drawn our Lewis dot diagrams. Now we need to figure out how they're going to get to their octet. Well, magnesium is going to likely lose its 2 electrons. It's going to be easier to take those 2 electrons away from magnesium than to add the 6 more that it needs to get 8. So it's going to lose 2, and that would make it a +2 charge. Now oxygen is going to gain those 2 electrons because it has 6 valence. It needs 2 more to make 8. So it's going to gain 2 electrons and make it a -2 charge. And then the last thing we need to do is draw our arrows to show the exchange of electrons. So there's 1 electron moving, and there's the other one. So after this happens, we end up with magnesium +2 and oxygen with our -2 charge, held together because of the attractions between the positives and the negatives. Next example, let's look at calcium and chlorine. Now, calcium, due to its location on the periodic table, we know has 2 valence electrons. Chlorine has 7. Let's look at what's going to happen. Well, calcium is going to lose 2 electrons because it needs 6 more, or it needs to lose 2. It's going to lose 2. That's easier. So it'll be a +2 charge. Chlorine only needs 1 electron, and it'll become a -1 charge. Well, calcium can give 1 of its electrons to chlorine, but it still has another electron to give. So we're going to add in another atom of chlorine. So now this atom of chlorine is the same way. It needs 1 more electron. So calcium can give its second electron to that second chlorine atom. So we end up with 2 chlorines, each with a -1 charge, and 1 calcium with a +2 charge. Okay, let's look at our last example. Let's look at lithium and oxygen. Now, lithium, based on its location on the periodic table, has 1 valence electron, and oxygen has 6. So lithium is going to lose 1 electron and make it a +1 charge. Oxygen needs to gain 2 electrons, and that will get it a -2 charge. Well, lithium can give its 1 electron to oxygen, but oxygen still needs another electron. So all we have to do is add another lithium. So in this case, we have 2 lithiums, each with a +1 charge. Oops, +1. And we have 1 oxygen with a -2 charge. So in our first example, we had one magnesium, 1 oxygen. In our second example, we needed 2 chlorines to go with our 1 calcium. And then in our last example, we needed 2 lithiums to go with our 1 oxygen. And that's how we make everything reach their octets. So let's look at some of these patterns on the periodic table. If we were to keep doing these, so remember that our number of valence electrons is the same as we go across the groups. So our first group has 1 valence electron, which means that it's going to lose its 1 valence electron to become a +1 charge. Everything in the second group has 2 valence electrons, so it'll lose its 2 valence electrons to become a +2 charge. Everything in group 3, remember we're going to skip the transition metals for right now because they're variable, they change. So group 3 over here has 3 valence electrons, so it's going to lose its 3 electrons to become a +3 charge. Now the fourth group is right in the middle. It has 4 valence electrons, so it can either lose its 4 or it can gain its 4 electrons. In the fifth group, we have 5 valence electrons, so we only need to gain 3 more to reach 8, so it's going to be a -3 charge. This group has 6 valence electrons, so it needs to gain 2 more to reach its octet, so it's going to be a -2 charge. Our halogens has 7 valence electrons, so they only need 1 more electron to reach their octet, so they'll be a -1 charge. And then our noble gases already have an octet, so they don't bond, and they're going to have a charge of 0. Notice our metals, so these are all metals. These are metals, these are metals, some of these are metals. All of our metals have a positive charge, because remember, our metals don't have a tight hold on their electrons, so they're willing to give their electrons away. So all of our metals have a positive charge, and we call those things with positive charges cations. Our nonmetals, on the other hand, everything over here, so these are nonmetals, nonmetals. All of our nonmetals have negative charges. And we call those things with negative charges anions. So our metals always form positive charges. They give up their electrons. Our nonmetals always have negative charges because they accept electrons. And that's how we look at ionic bonding.